Every introductory science course teaches a single, non-negotiable rule. Energy can never be created or destroyed. It only changes forms. To test that rule, imagine you are an astronaut drifting in the total vacuum of deep space. You wind up and throw a rock as hard as you can. Classically, that rock should glide in a straight line at a constant speed forever. But physical reality is different. Over massive cosmic timescales, the rock slowly loses speed, eventually coming to a dead stop. Light behaves the same way. A photon emitted 380,000 years after the Big Bang travels unimpeded across the universe to reach our telescopes. But by the time it arrives, it has lost 99.9% of its original energy. In the vacuum of space, there is no air resistance to slow the rock, and no friction to heat up the photon. That energy didn't transfer into the environment. It simply ceased to exist. Understanding how the universe breaks its own fundamental law requires looking back to 1915. It means examining the work of an unpaid mathematician who discovered a specific mathematical relationship that fixed a critical flaw in Einstein's greatest theory. In 1915, Albert Einstein was struggling to finalize his brand new theory of gravity, general relativity. While the concepts were groundbreaking, the math was incomplete. The early equations suggested a mathematical crisis. Total energy was not conserved. This violated the most basic principles of physics, leaving Einstein searching for a term that didn't seem to exist. Legendary mathematician David Hilbert tried to find the conservation equations himself, but even he was stumped. The best he could find were identities that only worked in a completely empty universe. Hilbert turned the problem over to his assistant, Emmy Noether. Despite having recently completed her PhD, she was working without pay or an official title. Noether faced an establishment that had explicitly refused to admit her as a student years prior. The Erlangen Academic Senate had argued that admitting women would overthrow all academic order. Operating outside the traditional academic hierarchy gave Noether a unique mathematical perspective. She approached the problem through the lens of symmetry, providing the mathematical proof that Einstein and Hilbert couldn't find. Noether proposed that conservation laws are the direct byproduct of mathematical symmetries. A symmetry is any action you can take that leaves an object or its properties unchanged. If you imagine an empty universe, its physics remain the same whether you are performing an experiment in one spot or shifting positions to another. This spatial translation symmetry means that an object in motion will maintain its speed and direction indefinitely. This is the origin of the conservation of momentum. Rotational symmetry works similarly. Rotating a system changes nothing about the underlying laws of physics, a fact that yields the conservation of angular momentum. Noether then identified the most important symmetry of all, time translation symmetry. This is the idea that the laws of physics are identical whether an experiment is performed today or tomorrow. Time translation symmetry is the mathematical parent of the conservation of energy. Energy conservation is a consequence of living in a universe whose physical laws remain symmetric over time. This connection explains the paradox of the slowing rock and the dying photon. Noether's math only guarantees energy conservation if time symmetry is present, but astronomers discovered that our universe is actively expanding and accelerating. Because of this expansion, the universe was fundamentally different 13 billion years ago than it is today. This continuous change means that on a cosmic scale, time translation symmetry is broken. Because the time symmetry is gone, Noether's theorem dictates that energy is no longer conserved. The rock and the photon lose energy because they are traveling through a universe that is changing as they move. Energy seems conserved to us because on the short time scales of human experience, time symmetry is practically undisturbed. We only notice the loss when we look across millions of light years. Noether eventually became a professor at Göttingen, but she was dismissed by the Nazis in 1933. Despite this, she continued to teach students in secret, hosting lectures in her own home. She eventually moved to America to teach at Bryn Mawr, where she continued her research until her death. Noether's framework for local symmetry became the foundation for the next century of discoveries. Her work led directly to the discovery of quarks, the Higgs boson, and the understanding that electric charge is conserved because of gauge symmetry. Noether proved that the fundamental forces of nature are the result of the universe maintaining its symmetries. Her math defines the relationship between the laws of physics and the structure of the universe itself,